Welcome back to The Explainer. We've had a lot of requests lately saying, teach me Unit 3 of the book Grade 10 Physics, and honestly, I am so here for it. Today, we're diving straight into the actual mechanics of how the physical world holds itself together. We're going to unpack the really fascinating principles of elasticity and the static equilibrium of rigid bodies. Basically, we're figuring out exactly what happens when forces act on the materials that make up our everyday lives and how massive structures somehow manage to stay perfectly balanced.
To get us started, I want you to look around you. Have you ever stopped to ask yourself why everyday objects act so incredibly differently when forces are applied to them? Seriously, think about it. Why on earth does a massive, heavy iron ship float effortlessly across the ocean, but if you drop a tiny iron needle into a glass of water, it immediately sinks straight to the bottom? Or how about this? Why is it that when you stretch a rubber band, it violently snaps right back into its original shape, but if you press your thumb into a piece of modeling clay, it just stays flat? Well, these aren't just random quirks of nature. They're actually governed by fundamental laws of physics that dictate the behavior of literally every single solid object on Earth.
So to uncover the physics behind all this, we're going to follow a four-step blueprint today. First, bending without breaking. Second, density and specific gravity. Third, stress, strain, and elasticity. And finally, the science of staying still. Let's get right into it. Okay, starting off with Section 1, bending without breaking, where we'll look at elasticity versus plasticity. Let's look at what's actually happening inside a material when you pull it or bend it. Because contrary to what you might think, solid objects, yes, even thick steel bars, are never perfectly rigid. If you apply enough external force, absolutely everything can be stretched, compressed, or bent. Now, there is a fundamental difference between elasticity, like that tiny spring inside your clicker pen, and plasticity, like a lump of potter's clay. When you push down on a pen cap, you're applying a deforming force, right? The spring inside compresses, but the split second you remove your finger, that spring bounces right back. That behavior is elasticity, the property of regaining original shape and size once the deforming force is removed. But take a lump of clay and squeeze it. It has absolutely zero tendency to return to its previous shape. It's permanently altered. And that is what physicists call plasticity. It's simply the ability of a material to be permanently molded or deformed by a sustained force.
But here's the catch. Even highly elastic materials have their breaking point. We call this the elastic limit. Go beyond it, and the material suffers permanent plastic deformation. Just think of a metal slinky. You can stretch it a little bit, and it springs back. Perfectly fine. But if you pull your hands way too far apart, the coils warp. You've officially exceeded the metal's elastic limit, forcing an otherwise elastic material to undergo plastic deformation. And this is a huge deal in the real world. Engineers absolutely must know the exact elastic limit of materials, like the heavy steel ropes used in cranes, because if they don't, that heavy machinery could permanently stretch out and become incredibly dangerous.
Moving right along to Section 2. Density and specific gravity, or simply put, why things float. So we're shifting gears a bit from how materials bend to how tightly packed their microscopic building blocks actually are. Density is basically just how mass is packed into a unit volume, just mass divided by volume. If we check the numbers here, water sits at 1,000 kilograms per cubic meter. Iron, on the other hand, is nearly 8 times that, at 7.86 times 10 to the third. And this brilliantly answers our earlier question about why a solid iron needle sinks. The iron itself is vastly denser than the water it's placed in. Giant iron ships only manage to float because their hulls are specifically shaped to enclose massive amounts of air, which lowers the overall average density of the entire ship to less than that of the ocean water. Pretty clever, right?
So knowing these density values, what happens when two totally different materials interact, like, say, an oil spill resting on top of the ocean? If you've ever seen a puddle mixed with motor oil or even just poured olive oil into a pot of water for cooking, you know it forms a separate layer right on top. This happens entirely because the density of oil is less than the density of water. It literally just lacks the compactness to sink down through the water molecules.
We can actually compare these values super easily using something called specific gravity. It's just a unitless ratio comparing a substance's density directly to a baseline standard, and that standard is usually pure water at exactly 4 degrees Celsius, which happens to be the precise temperature where water is at its absolute most dense. Geologists use this little trick all the time. They use it to determine the mineral content of rocks or to check the purity of a gold nugget without having to run any complex chemical tests. You literally just divide the density of your object by the density of water, and boom, you have your specific gravity.
All right, let's head into Section 3, Stress, Strain, and Elasticity. This is all about the science of deformation.
Now that we understand the actual materials and their density, let's look at the forces acting on them when we try to build things. In physics, when we talk about deforming forces, we use two very specific terms, stress and strain. The most crucial takeaway here is understanding this as a strict cause and effect relationship. Stress is the cause, it's the physical force you apply. Strain is the effect, the resulting deformation of the object. But stress isn't just about how hard you pull. It's the force divided by the cross-sectional area it's acting upon. Strain, meanwhile, is just a dimensionless number, measuring the actual physical consequence of that stress. Basically, how much longer, smaller, or twisted the object became compared to its original size.
And depending on exactly how you apply that stress, whether you're stretching a rubber band or squeezing a submarine down in the deep ocean, you're going to produce different types of strain. If you pull on a wire to elongate it, you've got tensile strain. If an object is being squeezed from all sides equally, which shrinks its volume, that's volumetric or bulk strain. And if you take a heavy book, press your hands on the front and back covers, and push in opposite directions to slide the pages past each other, you're causing a tangential shift, and that is known as shearing strain.
Which brings us to Hooke's law, named after the 17th century physicist Robert Hooke. Hooke figured out that as long as you stay within that elastic limit we talked about earlier, the harder you pull, the more it stretches. It is a direct, beautifully linear relationship. Stress is directly proportional to strain. And if you take that stress and divide it by the strain, you get a constant number that is completely unique to that specific material. We call this the material's elastic modulus. And when we're dealing with tensile stress specifically, it's called the Young modulus. To really wrap your head around just how strong some materials are, take a look at this massive number right here. 20 times 10 to the 10th power newtons per square meter. That right there is the Young modulus of steel. Because this number is just so incredibly high, it means it takes an absolutely gigantic amount of stress to produce even a tiny little amount of strain. This intense resistance to stretching is exactly why steel is the go-to material for heavy-duty machinery, the frames of skyscrapers, and those massive suspension bridges we drive over every day.
And that brings us to our final section, Section 4, the science of staying still. Let's talk about static equilibrium.
We've spent a lot of time talking about the internal forces of materials, but what about the external forces acting on entire macroscopic objects? How do we make sure a building just stays completely at rest? Well, for a rigid body to stay perfectly still, meaning no translating and no spinning, it absolutely has to satisfy two very distinct conditions of static equilibrium. If an object has a net force acting on it, it's going to accelerate in a line. If it has a net torque acting on it, it's going to spin. So, to be in static equilibrium, to be totally 100% stationary, both of those net values must equal exactly zero.
Let's look at an everyday example. Just a simple book resting perfectly still on a table. This perfectly illustrates that first condition, where opposing forces completely cancel each other out to equal zero. You've got gravity constantly pulling the book down toward the center of the Earth, but the rigid table is pushing back up on the book with an equal and opposite force, which physicists call the normal force. Because that downward pull and upward push are perfectly balanced out, the net force is zero. The book doesn't suddenly fly up into the air, and it doesn't fall through the floor.
Okay, but what about that second condition, the spinning? How exactly do we stop something from rotating when you have unequal weights involved? Like, say, two totally different sized kids jumping on a seesaw. The first condition of equilibrium is already met, because the pivot right in the middle pushes up with a force equal to the combined weight of the kids pushing down. But if the heavier kid sits at the exact same distance from the center as the lighter kid, that seesaw is definitely going to rotate. The secret solution here is all about controlling the torque. Remember, torque isn't just about the raw force, it's the force multiplied by the distance from the pivot point. So what does that mean for the seesaw? It means if you just move the heavier child a bit closer to that center pivot point, you actively reduce their lever arm. By doing that, the counterclockwise torque from the lighter child sitting far away will perfectly equal the clockwise torque of the heavier child sitting up close. All those rotational forces perfectly balance out to zero, effectively satisfying the second condition of static equilibrium.
So as we wrap up this explainer today, I want you to look around you with a fresh perspective. The next time you're driving across a massive suspension bridge, or even just sitting back in your office chair, ask yourself, is it the microelasticity of the materials inside or the macro balance of static equilibrium that's actually keeping you safe from falling?
It's a fun puzzle to think about. And once you see the physics holding our world together, you can't unsee it. Thanks for joining me, and I'll catch you in the next one.